All right, greetings everyone. Welcome to the first part of the video for section 8.1, getting on to our final chapter of this course. And yeah, let's take a look at what we're going to be dealing with here. So in section 8.1, we'll be looking at non-right triangles and different ways we can solve problems actually using trig, but in non-right triangles. So let's look at an application. So let's suppose we have two radar stations that are located 20 miles apart, and they both detect a UFO located between them. So in this picture, the UFO kind of looks like a plane, but we can of course assume that it's probably an alien of some sort of like flying saucer thing like that. Yeah. Oops. Okay. We're told that the angle of elevation measured by the first station up to the UFO is 35 degrees. So that would be this here. The angle of elevation of the second station is 15 degrees. And we want to know what the altitude is of the UFO. Well, altitude, if you're not familiar with that term, is distance above the ground. So in this case, that means we're looking at the length of this line right here. And I'm going to call that, it says altitude, so, but it's really like a height above the ground, so I'm going to call that h. And let's think about how could we go about solving for the value of h? Well, based on other things we've learned this quarter, one approach would be to look for a right triangle, which it looks like we could have one like right here. And we know the angle opposite the side we're looking for, so that 15-degree angle. We want to find the side h here. And we have to look for other information that we know in this triangle. And it might be really tempting to say, oh, the 20 miles here is the side adjacent to the 15 degrees in that triangle. But notice that's not true, right? Because the adjacent side of that 15-degree angle would be just this side here. But the 20 miles is the whole distance between the two satellites, so that won't work for us. And a similar thing would happen if we tried to create a right triangle using the other side, the other half of the bigger triangle, so this piece here. And again, we know this angle here across from the side we're looking for. We try to find h, and you might think, oh, again, the 20 miles is the adjacent side here. But again, that doesn't work. So we need a new tool for solving problems like this one. So let's take a look at what that tool would be. So we're going to use something called the law of sines. And what we're going to do here is see where the law of sines comes from. Now, this process we're about to do is not something I would expect you to have to do on a quest or even potentially a project. But I do want us to see that math formula don't just fall out of the sky, that they come from somewhere. So looking at this picture we have here, notice we have a triangle. Okay. And of the one I just highlighted in pink there, hopefully you would agree with me that doesn't look like a right triangle. So our ratios like sine, cosine, and tangent usually will not work in that triangle. However, notice if we drop this altitude here, this length h, then it divides our triangle into two smaller right triangles. And so I want to focus on those. So we have the one here on the left that I'll highlight in yellow. And I don't know why that just happened, sorry. And then we have the one on the right here that I'll highlight in red. And oh my goodness, I do not know what's happening. Oh my Lord. Okay, let me try this again. Nope. All right, there we go. There's a red triangle and the yellow one. Okay, and what we're going to do is set up a ratio for h in each of those triangles. So in the yellow one, notice we have an angle alpha here that has been labeled. The side h is labeled and the side b here in that right triangle. And notice in that yellow right triangle, the side H is opposite the angle of measure alpha, and the side B would be the hypotenuse. So we have the opposite and the hypotenuse, which tells us we could set up a ratio for sine of this angle. So sine of alpha equals the opposite side, which is H over B. And if we do a similar thing in the red triangle, so again, we have the angle beta here. The side H looks like it's opposite. The side A looks like it's adjacent. So we could again, or excuse me, the side A is the hypotenuse. So we could set up a ratio here that is sine of beta equals, again, the opposite side, which is H, over the length of the hypotenuse, which is A. So now we have these two ratios. And then what we're going to do in each of these is solve for the variable h, or isolate the variable h. So in this first equation, we can do that by multiplying by b on both sides. So cancel, so we end up with h equals b times sine of alpha. And then in the second equation, we can multiply by a on both sides. And when we do that, we end up with h equals a times sine of beta. And what this leaves us with then is h equals this and h equals this, right? So what we could do, for example, is take this expression here, and since h equals that, we can plug it in for the h over here. So that would give us one big equation now that would look like a times sine of beta equals b times sine of alpha. And then what we're going to do is divide the sides out, the lengths of the sides to each side. So I'm going to divide by beta here, divide by beta here. So these betas will cancel. And so what we have now is sine of alpha equals a times sine of beta. That's supposed to be a beta. Over b. And then we can divide the a out on that side and divide it on this side as well. And when we do that, what we end up with then is sine of beta over b equals sine of alpha over a. And that there is our law of sines. Okay. So we actually don't end up with h in there at all. But it does give us this new equation. So we have that sine of beta over b equals sine of alpha over a, which is kind of cool. Maybe not something you expected. All right, so let's take a look more at this sine, or this what we're calling law of sines, a little more generally. So here we're given a triangle, and in this case it doesn't matter whether it's a right triangle or not, with angles and sides opposite as shown. And in this picture we're looking at, they use the angles, or the letters alpha, gamma, and beta to label the angles. But when you use the law of sines, you don't necessarily have to have those labels. Here's what's important. Is notice here in the formula it says sine of alpha over a, sine of beta over b equals sine of gamma over c. And notice in each case how the angle, the position of the angle in the picture, relates to the side that it's paired with in the formula. So we notice that alpha is right across from the side A. Beta is really straight across from the side B. Gamma is right across from the side C. And we see them all paired up over here. Okay. So what this is really saying is that if we have some sides and angles labeled in a triangle, then the side of an angle, or sorry, the sine of an angle over the length of the opposite side would be equal to the sine of any other angle over the length of its opposite side. Okay. And so as an example of that, just kind of another example, let's say my triangle was this yellow one here. Let's say I had a theta here. And what's another? Let's say I have an x here. And I'm going to label this side as, gosh, I can't even, I'm not thinking of letters right now. Call that capital A and that capital B. Then the law of sines tells us, based on this, the sine of the angle x over the length of the side capital A should equal the sine of the angle theta over the side length of side capital B. So again, notice that the letters don't matter as much as the positioning between the angles and the lengths of the sides. Okay. All right, one more thing I'll say about this is generally when working with the law of sines, we are working with angles measured in degrees, but not always, but most of the time we are. Okay, that's it for now. Thank you for watching.